Jim. Welcome back.
Hi, Jim. Yeah, welcome back.
I'm back.
Well, okay. So
I was talking to Arthur when I was in Poland. So, but I didn't met Pavel. Yeah.
Oh, have you? Okay. Yeah, he's on the call. And so here, let me share my screen.
Jim, how are you?
Awesome.
Are you feeling rested?
Yeah, pretty much. You know, I wake up every hour. We have a new chime clock.
Oh, okay. So if you go into Discord, at the very top under General Member Channel, there is so here's the list of events. So let's see here. Well, they've well, I'm not seeing it there. Hey, Gary, let me do this a different way. Let me pull up the Archain calendar.
Hey, Steve, Thomas Love, Jim.
Hey.
Where's Dan?
Not here yet. Okay.
I think it's on the calendar, right?
Yeah. So on the calendar. So I have New York time calendar. So there you go. So it's right here, the developer stand up, and that's the Zoom session. So and that session is not recorded, but you get all the developers in Poland. Kent Shikama's on the call. Greg's always on the call. So it's the whole Archain development team, and they have a meeting for an hour, and you get to understand the state of the Archain development. What they're working on, what challenges they're having, how they work through their issues, how they work together. It's a neat environment to be in.
Yeah, Pavel told me that they're totally distributed. So yeah, I would love to hear what they're planning and what they're doing. So
yeah, and for me, it gives me a sense of confidence that, hey, we're going to get there. We're going to get to mainnet when you see everything that they're working on, and how things, and you get an appreciation how big of a project and complicated of a project all this is. Yeah. So good. So I guess Dan had commented in Discord that he at least last week, he was interested in showing everybody his Idris work that he's working on. I'm not sure exactly what that is, but hopefully he'll join us and kind of enlighten us all with.
And he was planning this for today, or because I was not sure.
Hey
Dan.
There's Dan. Hey Dan.
Good morning.
Hey.
Good morning.
Morning. Good to see you.
He's going to grab a guitar. Nope.
Be right back. I need to get coffee.
Okay.
I was hoping he was going to grab a guitar and give us some more Archain blues.
Archain blues.
Backlighting's not good on video. I don't know if this lighting's all that good either. Anyway.
Dan, I loved this explanation of object capabilities, and when you were covering Mark Miller's video, so that was very helpful for me.
Oh, cool. Yeah. So this Idris stuff, there's a certain part of it that I can't that he asked me not to distribute. So I could either cover everything except that, or we could not record.
Why don't we not record part of it? Can we do that?
Probably.
Just give us an introduction, then I'll stop the recording.
Okay.
And maybe, Dan, if you could provide a context for this work and how it sort of fits into the greater scheme of things, if that is in fact, you know, a part of it, or if you think it'd help us to understand.
And also, why Idris?
Yeah, those types of questions are very interesting.
Okay. I wonder why my screen went kind of dark when I started sharing.
Yeah, I also see it a little dark.
I'm going to try to stop share. Share screen. Desktop 1. Share. Okay. Okay. Why Idris? I'll maybe put it on more familiar ground. Okay, where'd it go? Right.
How this is similar? Yeah, how this is similar to this latest work?
Right. Well, okay. So when I am faced with a paper like this, so there's all this stuff that looks like formal mathematics, right?
Right.
But when you look at the source code to it, it's not. You can't compile this, or you know, the only kind of syntax errors you get are, well, it didn't format nicely when I printed it. But if the logic here is bad, the computer won't actually tell you. So this is kind of a picture of the mathematics, but it doesn't actually convey the mathematics. So for me to convince myself that I understood the paper, I would go, let's see. I don't remember how this works. There's some, no, that's not the one I wanted. There's some key sequence where I can get it to line up right.
So what Greg was talking about is not something new, right? Because you have it on your GitHub from last year.
Say again?
This is not something new that Greg presented, this theory of graph languages. Right?
Well, my understanding is that it was new as of some years ago, or you know, whenever he made it up.
Okay.
How do I get it so that it's only showing the stuff on the right here?
You can definitely use on the center. You can use arrows to move it to left or right. But I'm not sure if there is a preview. The preview is in new version, but in this version I'm not sure.
All right. Okay, so so there's been a few different languages that I've used to try to, you know, check my understanding of papers, but the current one that I use is Idris. It's a dependently typed programming language. Has anybody ever used Agda?
Yeah, I played with Idris a little. So
All right, so there's AGDA, if you're familiar with that, and there's another thing called COQ, C-O-Q, which is more mature. But COQ is more meant for doing theorem proving and less for doing practical programming. Idris is kind of on the boundary of both. When you're Idris programs, it's like Haskell, it's a programming language.
and Idris is mostly using mostly syntax from Agda, right? And from Haskell, right? Idris uses syntax from Agda and from Haskell, similar syntax.
Yeah, I don't know Agda very well, so I don't know which parts it grabbed from Agda.
I was listening to some lectures about Agda. So.
Okay. All right, so module graph is just like Haskell. Anyway, it's saying, okay, that's the name of my module, and I'm going to use stuff from the standard library, list and quantifiers. That's for saying something like for everything in a list, this is true or something. And Idris has a totality checker where if you write a function that doesn't cover all the cases, or a function that could loop infinitely, or that it can't prove won't loop infinitely, it'll say, I'm not sure that function is total.
So you can define like responsive function, or how they call it, productive function, right?
Well, you can write partial functions. I think Agda, you can't do that. I think
no, I mean productive function. Productive in the sense that it will never stop.
Oh, right. There's things that they have codata. They have they have codata where you always have to generate data instead of always consuming data.
So are there there's now they have construct for codata? You are saying that because I didn't find it before.
This is kind of jumping into the deep end early, but
oh, sorry, but
we'll go aside from here.
oh, cool.
Yeah, so if you want to write an operating system or something where you don't really want your operating system to terminate,
Yeah.
or a web server or something, you don't want it to terminate, but you still want to be able to prove that it does the right thing.
Nice. I didn't know that they have codata now. Cool.
Okay. So I'm reading the paper, and where did I see? Two graphs must be disjoint or something. That seems pretty far down there. Let's see, what's the first thing I did was, sometimes I try to make it so that the syntax in the paper looks a lot like the syntax I'm writing. I haven't really managed to do that very well. But so let's ignore this and ignore this for just a second. Okay, so graph expression. It says data, graph expression, two types into another type, where, blah, blah, blah. And this is how you kind of make judgments. Data types and judgments end up being the same thing. And so where's graph expression over here? Okay. So, right. So this is sort of you'll see these grammars or inductive definitions or whatever in lots of papers and stuff. And it says, okay, there's zero, the empty graph are just empty. So I call it empty. And data constructors are traditionally start with an uppercase letter. And okay, so I'm actually using my shorthand here. G of X and V is actually short for a graph expression, X and V. So in other words, empty is a graph expression. If you've got a vertex and a graph, you can adjoin the two and you get a new graph. Well, you get a graph expression anyway. Then there's actually two different kinds of adjoining that.
So you're saying this pipe is not like a par, right? There is a left and right for this operator, right? This is not a par, like a parallel.
I don't think what words are you saying? I don't think I'm hearing you.
Like a par in rolling. Par.
Oh, okay, right. Yes, this vertical bar means something else.
Yeah, okay. Because there is a left side and right side. You cannot interchange. It's
right, yeah. If you wrote G bar V, that would mean some nonsense.
Okay.
Well, or maybe it would mean adjoin on the other side. I'm not sure.
Okay. Nice.
I don't think there is adjoining on the other side.
So you're defining this X and V as a types. Your data graph expression is parametric in these two types.
Right. Yeah.
You're not saying I have concrete type. You're saying for any type.
Right.
Mm.
Let's see if he says anything about that up here. Yeah, it's dependent on a theory of variables X and a theory of vertices V.
Okay.
Each theory is required to provide an effective procedure for defining membership. Now, I didn't state that, but there's a way to say that in Idris, which is they've got a decidable equality.
Oh, Dick.
Yeah, so you say DESEQT or whatever you want to say that it's got an effective procedure for deciding membership. If something's decidably equal, if given a claim that something's a T, you can either prove that it's true or prove that it's false.
Okay.
But I didn't put that in here. I could have said DESEQX and DESEQV as constraints up here. Probably should have or whatever, but I didn't. I don't know if I didn't end up needing. Anyway, so I don't know if I want to go through this paper in detail because, but I hope you get the general idea that, you know, when I'm reading a paper like this, I did get, it was somewhat satisfying. So I went through and, you know, transcribed each of the definitions and stuff like that. And then get down to some examples. Does it? Okay. The discrete graph. I guess the discrete graph of 0 is just the empty graph, and the discrete graph of n is n adjoined to 0. And then what's that operator? How do you read that operator? Juxtaposed with the discrete graph of n minus 1. And so I could write that here, and you can actually go into a command line thing and say, okay, show me the discrete graph of 3, and it'll compute for a while and then actually print it.
Nice. Yeah, this is very nice definitions.
Yeah.
Yeah. And that is exactly the type level, like a number, right?
Right.
Nice.
Yeah. So the
This
discrete.
looks very, very good. I mean, it's almost the same as mathematical definition.
Right. Now, if you make a mistake over here, the computer will tell you, right?
Yeah, yeah.
And of course, I made hundreds and hundreds of mistakes. And what usually what I learn is when they're being implicit about something.
Mm. Yeah, I was trying to write for raw calculus graph, reduction graph, and yeah, this is the same problem. You write something and you would want to know just is the type check. This is the
Yeah.
first thing.
I did end up trying to read the row calculus paper, doing the same thing. I didn't get very far on this, and then I discovered that Greg had done a OCaml version of the thing, and I would have, would have been just the same thing. Anyway.
Did you see my Haskell versions? I have like 5 versions.
Oh, 5 versions in Haskell, you said?
Yeah.
I might have seen one of them. I don't remember.
I was trying, different with type classes, without type classes, But now I want to try something like you have this in Idris to be parametric in both name and processes, like two different types.
Oh. Well, I thought the whole trick with row calculus is that it's not parametric because you use quoted processes for names.
Yeah, but I don't. So if your data type is recursive, you must all of your functions will be recursive for this data type. But if they are parametric in both types, I'm planning to use recursion schemes to abstract just the recursive part.
Okay, well, I guess
that's why I'm interested in your definition in Idris with these two parametric types, X and V.
I see.
Nice.
Right. Yeah, in Idris, you have to define things before you use them unless you put them inside of a mutual block. So when I was doing name and process, yeah, they depend on each other mutually. So that's how I did it when I was doing this. Anyway. Then, so there's Agoric folks that are trying to do smart contracts with capabilities, except they're using JavaScript, where our chain is using Erlang. And Mark Miller is not real big into formal systems, but he kind of appreciates the value of them, and he collaborates with people who are deep into it. And anyway, he's got this sort of semi-formalization of his electronic rights transfer protocol. And then they've got a paper. Well, there's a series of things. These are the old papers. Formal reasoning. Hang on just a sec. Just a moment.
So you're, how do you take into account semantics of existing? Well, this is not the whole JavaScript. This is only part of the JavaScript. How do you express semantics of this part of the language that you want to go for?
Well, they did all the tedious business of defining a JavaScript-like language. In fact, that's the part where I'm a little bit stuck. Okay, so issues. Here we go. So I asked, so he gave this San Francisco Blockchain Week talk, which I've referred to many times. We went over it in one of these sessions. He mentioned chainmail. And so I guess this is one of the papers. And then he wrote to me, then actually, now is a good time to stop recording. So So this was the lookup. But the idea that I ended up getting stuck just having finite mappings from like identifiers to values and stuff. Oh. So this is where I sort of ended up getting stuck. The idea is, okay, so if you've got some dictionary or mapping or whatever, and you insert the pair KV into it, and then you look up K, you ought to get V, right? But I couldn't prove that. And
what exactly do you need to prove? That there is no operation in between insert and lookup, or
no, I just need to be able to. So the type signature is just that this returns an option V, and that it could return none, right?
Yeah.
Unless you actually specify. It's like the Haskell data type for sort. It just goes from list of A to list of A, right?
Yeah.
So the type definition doesn't guarantee that what you get back is actually sorted.
Yeah. But how can you you must prove that no one else touched the same key or changed the same key, right?
Something like that. I mean,
between these two operations, insert and lookup. Right? This was what I was thinking. But or there is there some other way?
It's just that you have to sort of not lose the information while you're at it.
Mm.
So there's two different ways to write functions in Idris, maybe in Haskell. When you're going to say, okay, is this thing an element of a list? You can either return a Boolean true false, at which point you lost all the information about, for example, where the thing is in the list. Or you can return a proof that the thing is in the list, which is like if it's the third item in the list, it goes, okay, not here, yes, here. That's the proof. It's sort of a constructive proof that the thing is in the element of the list. Let me see if I can find where they do this. Prelude. By the way, I don't know. Okay. Yeah. So there's in this case, they've got this thing called semigroup, and the formal properties of it are only in comments, right? But you can actually write those formal properties in Idris, at which point you have to prove that the thing is a semigroup in order for it to be a semigroup. So let me show you that version of it. I think they put that in contrib or something. So there's functor. We'll go with functor. It's close enough to semigroup. It's one of these real basic things. So something's a functor if there's some identity element where given a function.
You want to prove that map ID is equal ID. Right.
Right, so it's the first one in the type classopedia. Where do they give the laws for functor? Oh, here we are. Fmap ID equals ID, and Fmap of G compose H is Fmap of G compose Fmap of H. So that's identity and composition spelled out in Idris. So, A.
And you say that in Idris you can write functions in two ways. I mean, in Haskell, there is like a special syntax for type level functions, but in Idris, are there the same?
It's not different syntax. It's just
saying they're not the same.
They are the type level functions and regular functions are the same syntax. They're just functions. Right, but the type here of fmap is just going to, here, give me a function and a list, and I'll give you back a list of B's. But that definition of fmap doesn't actually tell you that, oh, that's an instance, sorry.
Yeah. Yeah, you can write instance that that doesn't hold the lobs.
Right.
And in Idris, you cannot.
Well, there's two different versions of functor here. So this is the one where you have to actually prove that your thing is a functor, and you can't get it wrong. If you have a verified functor, then it necessarily follows the laws.
They have separate verified functor. Okay.
Yeah, you can express both notions
Cool.
using the same syntax. So prelude, algebra, where's functor? What am I doing wrong? So you can just write just like in Haskell.
Okay.
And so to have one, you can have one of these that doesn't obey the laws.
Okay. I was thinking that all functors must hold the laws. That's okay.
Right. Only if you define functor that way, like they did in the verified functor one. So similarly, you can have so here's their list construct. There's nil and concatenate or cons basically. Non-empty inbound length index tail. Hold on a sec. Okay, sublist. No, that's not what I'm looking for. Okay. So this element function says that, okay, if I've got some equality predicate on A, because it's not necessarily on every type, you can compare them, but that's the same as Haskell. If I've got some thing of type A and a list of A, I'll tell you whether that A thing is in that list. And I'm just going to return true or false, right? This is just like Haskell. It's going to say if it's the first element, great, and if not, look in the rest of the list. Now, where'd it go? Oh, data list. Okay. So now they've got a data type or a judgment or whatever. That's the proof of that something's an element of the list. And so here is a proof that X is the first item in a list. And there, if X is in X's, then there of that proof gives you a proof that it's in later. So, in other words, if you can prove that X is in X's, you also know that it's in Y concatenated with X's.
This is like a nested type for each index in the list.
Right.
And how do you say it's not in the list?
That's exactly what comes next. It's kind of interesting.
Oh, it's not part of this data type, or it's possible. So yeah, okay.
So this is kind of interesting. So there's a thing called reflection, or
Yeah, I was just listening in Poland on one lecture how to implement dependent types, and this guy was talking about REFL.
right. So x equals y is actually a type, and the way that the only member of that type is REFL, or REFL of x for each x. So
it's a little weird type. We had discussion on the lecture. You know, how to interpret this. You have x, and you are saying that x is equal to x.
Yeah. In some ways, it's completely normal. If I just make a new thing, thingy.idris, and I say data equally type I guess it's two things.
You need a column after the name, I think.
Can I get the same number of L's? Let's just go with twos. So that's a perfectly reasonable definition. It's saying, okay, there's a data type that's parameterized in two things. I guess they would do this. They would name them. And the only way to exhibit such one of these is if the two somethings are actually the same something, right? And all they do is change this to, I think they reserve the section, the syntax, but that's all there is to it. Okay, and so this impossible thingy is basically saying this can't pattern match. And not is kind of interesting. I think it's not x equals x. Yeah, so void is the empty type, and if given an x, you can exhibit an element of the empty type, then there must not be any x's. So this is basically saying that this can't pattern match. Let's see if I can unpack that a little bit. Here equals there of something.
So you cannot construct the empty list, right? There is no way to construct it.
Right, and it's not like some kind of heavy-duty theory thing of should just be we should just be able to look at the syntax and realize that no, it never happens that way. Here is not there. Here will never equal there. I think that's sort of, in general, if you have data X, and then you have a couple of constructors, then in general, C1, equals C2 is never going to happen.
I'm thinking, what operations do you have on this data type? Can you do you have something like intersection or no intersection, something like?
No, these are just ways of forming terms. And equals is saying that's the same term. And if you have two different constructors, you definitely don't have the same term. You can just stare at it. Nope, not the same thing.
Oh, no, I'm talking about this element data type for list. I'm thinking, can you be in situation that you remove the last element and then you end up with empty list? This shouldn't be possible, right?
Well, the only thing you can do to create an elem is you can either have a here or a there. Those are the only ways you can make one of these things.
And what operations for this element exist?
That's it. All you can do is construct them and take them apart again. You can construct them and you can pattern match against them, just like any other Haskell data type. Okay, so that's just saying sort of obviously those two terms are not the same term, and then this says if the tails don't match, neither will references to them. So if you have not this equals that, then not there of this equals there of that. F of REFL is F of REFL. I could probably unpack that for you. What's kind of fun is that the Idris knows a little teeny bit of theorem proving, so it would probably find that one for you. There's this whole book called Type-Driven Development.
Yeah, from this author of Idris, right? Brady, Edwin Brady.
Yeah.
And I wanted to ask you about writing proofs in Idris. You're using the new syntax, right? There was like old syntax for writing proofs, which was more similar to Agda, but now this is like a little different.
All the stuff we've seen so far, I think they don't call this writing proofs. They do have a tactics language, which I've never used.
Oh, I see. Okay.
Oh, I guess they deprecated this whole thing. Yeah, you can do intros and rewrite and blah, blah, blah. Attack.
Yeah, I was listening somewhere that now you can use this like Idris syntax to write proofs. Yeah, and they have this elaborator reflection. Yeah, you are using this elaborator reflection, or?
I did because there was something that got boring, and somebody said that they. Where'd it go? Oh, I was using it. Maybe I'm not anymore. So yeah, the elaborator is basically quoting and unquoting, and so it's macros.
Oh, I see.
And so I got bored of implementing this repetitive thing, and somebody said, "Oh, somebody's got a thing that will do that for you." They've got some macros for that.
But this is probably completely typed macros that also you can use like a proof that.
I'm not. Let's see. I think the macros, they're hygienic, but you know, what happens is, you know, it takes some syntax in and makes some syntax out, and then the compiler, you know, checks the resulting syntax. And if you got any problems with the results, then of course it's bad. But I'm not sure what happens while you're doing the, well, I guess the elaboration is, where did that go?
But you're saying that for most of the stuff you don't need this kind of way of elaboration.
This is what I was using. Do notation is part of Idris. That's kind of interesting. They're using the proof stuff in the normal syntax.
Yeah, and how do you parse this in your head? I mean, do is just as a syntactic sugar for bind.
Yeah.
But how do you know, what does it mean when you write proof inside the do notation? Is this like a bind inside of this monad, or?
Let's see. The TT name, I suspect, is a quoted expression, and there's some kind of a lab monad, maybe.
Oh, I see.
This is head spinning stuff. I have not really learned how to do this. I just used it.
Cool.
But this is, you know, make right hand side and.
Oh, I see. In a sense, you're creating Idris terms.
Yeah, yeah. It's just messing with syntax.
Oh, okay.
It's taking apart terms and making new terms, putting them back together and stuff.
Yeah, this makes sense. Yeah. But yeah, do you have to know all the Idris semantics and the whole AST, or are you working with the same AST as, you know, the Idris compile time?
I believe so. Like PT name is what the compiler uses, I think.
Oh, okay.
TT is their like core theory or something. I can't remember what it is.
Oh. I think I saw Elab
You saw
on the list. Yeah, it's a third list. Oh, that's cool.
yeah, it's a little bit freaky how much of this stuff is not magic. It's just written in Idris.
Yeah.
There's a reflected elaboration script. I don't really know what that means.
Yeah, but when you look this, all of these constructions, you know, I'm not sure what they mean.
Right.
Okay.
Meanwhile, back on planet Earth, so I was trying to talk about the fact that you can have a list function that says, okay, a sort function that says, okay, give me a list and I'll give you back the list. And then in the comments, it'll say this is sorted. Or you can actually, in Idris, you can actually have a type that's sorted list. So this is import sorted map. Yeah, now I had a problem with this because it says sorted map, but it doesn't actually sort of have any formal properties that are written in Idris. Again, that's sort of in comments. Okay, so I reported this problem. I said, okay, when you call the lookup function, it doesn't actually sort of it loses a bunch of information about what was going on. And I found this in the Coq standard library. It says that E maps. It says Y maps to E in add. Let's see. It says that if X and Y are equals, then Y maps to E in add EXM. In other words, if you take M and add the pair X goes to E and Y is equal to X, then Y maps to E. Now the equals part I think you can skip in Idris because I think that has something to do with Coq's logic. Anyway, that looked an awful lot like this to me.
Yeah.
And I actually got a response from the guy. He says, Dict and friends are wrappers around an improved structure, so I have to look at AVL tree, and this is what I've not done yet. But he does have data, AVL, tree, is this B tree? Import data.avl. Oh, here we are. Hang on, I'll find the part. Okay. So just like we had the elem thing that said that some element was in a list, this says that some key is in the tree is in a tree, and their trees are trees where each node is a key and a value. Let's go back and do that a little bit more slowly. Oh yeah, let's just sort of read this through. We'll skip some parts. But so there's this judgment or data type balance that says basically two natural numbers are within one of each other. So this is saying that if you can have left heavy, and that gives you, that's a constructor. It's a zero error constructor. It's just a thing. It's just a thing you write down. You say left heavy, and that proves that n+1 is balanced with n. And you can write down R heavy, and that proves that n is balanced with n+1, or the successor of n, and obviously n is balanced with n, and that's just balanced. And then we got some function height from balance nm to natural, and height of some balance thingy is the successor of height prime of B, where height prime of left is 1 bigger than n, height prime of right is 1 bigger than n, and height prime of balanced is just n. Indirection ensures that it reduces to at least S of n. Oh. This is basically saying you don't, generally when you prove things about natural numbers, you prove it about 0, and then you prove it about the successor of any number. But you've got some comment that says you basically never have to consider the 0 case. I'm not exactly sure why not, but I believe it since it compiles.
Yeah.
I don't know if anybody else is trying to follow along, but okay. So that's a reasonably straightforward bunch of Idris. Okay, so here's the core data structure. So given a key type and a value type, tree gives you a new type where empty is a tree of K of E, and given a key and a value and a left tree and a right tree will give you a new tree.
What is AVL?
This is a sort of well-known thing. I can't remember what AVL stands for.
Yeah.
Oh, Allison, Velsky, and Landis.
Okay.
To self-balancing. It's basically a tree where the depth is kind of almost the same everywhere. This one's kind of odd looking. I thought they were all within one of each other. Anyway, this is a very well-known data structure. You can, read all the Wikipedia about it.
Yeah, yeah. Okay, so this balance represents indices in this tree, right?
Depths.
Or depths, right? Or depths.
Right. Okay.
Okay.
So this is the tree type, and that's pretty straightforward. Just each node has a key and a value, right? You've either got empty or you've got a key and a value and a left and a right. Pretty basic. Yeah. It's a binary tree where the types of the trees are key and value pairs,
Yeah.
roughly. Okay. And then what makes something, as opposed to an arbitrary tree, what makes it an AVL tree is it's either the empty tree is AVL invariant at 0, and then if your left and right are AVL invariant, and B is some balance NM. In other words, your left tree is within one of the heights of your left and right tree are within one of each other. Then you can stick them together and you got an AVL tree.
Sorry, can you say that again?
Right. Okay, so the AVL invariant is that the left and right of each node are within one height of each other. So the empty thing is obviously AVL invariant at height 0. That makes sense, right?
Yeah.
And then if you've got two trees, one of height n, one n AVL invariant at height n and one AVL invariant at height m, and n and m are within one of each other, because that's what the balanced data type means, right? B is a proof that n and m are within one of each other.
I see.
Then
so in each node you have exactly the type, and this type tells you what is the depth of the left side and what is the depth of the right side.
Right. This height is a natural number here, yeah.
And so when you constructing the node, you from this balance you get. Oh, you are holding this b as height. Oh, you can calculate height from the balance. Okay.
Yeah, height of B.
Okay. Okay. Can you go to the height function? This is a type level function. It is used as type level.
Well, it's just a function. Everything's
Yeah,
type level.
it is just a function. Yeah. Okay. Okay.
Yeah, functions, you look at them as constructed proofs of their types. Okay, so an AVL tree is the subset of trees that are AVL invariant. And subset is another one of these things that blows your mind because it's like 3 lines of Idris and you're like, what is that? What is that? How does that work? Dependent pair where the second field is erased. So you've got some type A and some function from A to type. That's basically the way I write predicates. Then I'll give you a type back, and the way you can exhibit, the way you can give a proof of subset A, P of A, is to.
What is this? Is there a dot before parentheses? What does it mean, this dot?
I don't know.
And there is also dot on the first position in evidence. Strange things. You're right. They are very simple and strange.
In some sense, it makes sense, though. This is saying if you have X of type A and you have P of X, sorry, you have a proof of P of X, then that gives you a proof of subset AP. What the heck does that mean?
And you're holding this type and also the proof in this new type.
Well, okay, so it sort of makes sense. If you have P of X, then X must be an element of the subset of A such that P.
Oh, I see. If you have the subset with this proof, this A must be as part of this. This proof exactly tells you that A is the subset.
Right. Well, it tells you that X is in the subset of A such that P. You read this as the subset of A such that P. Like, you know, right? Like the subset of integers such that they're even or whatever. If P was even. So it's the subset of trees that are AVL invariant for some n.
And what is the example of a tree that is not AVL?
If you had So your keys and values are like letters and numbers. And then on one side, let's see, on the one side is nothing. And on the other side is empty again. Ah, man, why is it doing this? So this is depth 3 on the right-hand side and 0 on the other, or depth 2 on the right-hand side and 0 on the other, this node here.
Okay.
So those are not within one of each other. You know, I guess this one's empty, empty. Ah. Yeah, that's really nice. Right, so this guy is balanced because his children are both empty, so those are both level 0. This guy is cool because he's got 0 on the one side and 1 on the other side, but this guy has got 0 on the one side and 2 on the other side, so he's not cool.
How do you mean 2 on the other side? Oh, to
Depth.
To depth. Oh.
Yes.
Okay.
Now this is kind of useful because when they do the insert, this gives you, this is kind of an interesting function here. So they're gonna have a new judgment or data type called insert result, where it's either the same, so the output is the same depth, or we're going to say that it grew. So if you've got an AVL tree that's one bigger, then so there's 2 different kinds of insert results. One is same and one is group, and they both.
This means that you, in one case, you have already key and you're replacing, and in others, you're inserting new.
Well, it could be that you're replacing a key or you're replacing an empty.
Oh, okay.
I think. We'll see. So that's a data type or a judgment. And now we're going to make a function that, this is interesting. It takes an insert result, process the result of an insertion of a new key value pair into the tree, returning the new tree and a proof of the tree's new height. Oh, I think I know what's going on. They're going to have some function that you're going to, it's going to basically generate one of these insert results, but then you actually want the tree. So this thing is going to take, it's going to run the insert result and actually give you the tree. And it's going to give you a pair, and a dependent pair is written that way. And in the P, you get to use X. And this is basically, you can say there exists X such that P of X. So this is going to say, it's going to return an N such that AVL tree NKV. Oh, basically it just takes this thing apart. Run and sort was it same T, it's going to give you, oh, whoa. The underscore means that the compiler figures it out for you.
And this makes sense, right? Because you have n in the first place.
Yeah. Right. And then left rotation and right rotation are probably in here. So left rotation, boop, see what they did?
Oh, now I see that RL trees are often compared with red black trees. I was watching some lectures about red black trees. I was thinking that they are very similar. Okay.
So perform a left rotation, takes a key value, an AVL tree of height n and an AVL tree of height n plus 2, and gives you back an insert result of n plus 2. Impossible because blah, blah, blah. And it goes through a bunch of cases. I'd have to think hard about all that stuff. And then we got right rotation. It's basically saying a left rotation is when you got something that's out of balance and you want to get it back in balance, I think.
And in this rotation, you are getting this result, right? Instant result.
Yes.
And how is possible that it grow? Because you are just rotating, you are replacing stuff, right? What does it mean, grow, in this situation? You must create another empty node somewhere because you moved.
Okay, so this is saying, here's a case that returns grew, all right? It's saying if you got a key value and AVL tree, how is this match up with this? I don't understand what that means. Hang on. Where's elements? So that must be imported from somewhere. I don't understand that. Hang on. Because, oh, now I don't see. Okay. Key is type K and val is type V. And L, this one's L, AVL tree. And then, oh, element. That's the subset thing. Now I remember. Right. An AVL tree is always some tree and a proof that that its heights are okay. Right? Okay. Right. AVL trees of this, and the only constructor for subset is element, right? So this is, right. So empty is an element of
this proof, right?
Right.
Oh, I see now.
Okay, we were going to look at GRU. All right. So we've got key value, and we've got some tree L, and it's proof that it's invariant, that it's happy, right? And then that's this one, and then this one. You got some other key and value, and left and right, and a proof. That it's happy.
So we are extracting these three things from proof, right? So we can use it in our new constructed proof.
Right.
But we have this R.
So if I take this and write it the way you might write it in Haskell, let's see. In Haskell, you wouldn't have the proofs, the proof terms along with it. We'll leave the GRU in there for a second. Okay, so if we leave out the proof terms, what we're saying is that if you want to rotate left, given key value, a tree L, I guess that's the left, and then here's the right tree, and then the right tree's left and the right tree's right. Then to rotate that left, you put what was on the right at the top. So we can make a picture out of this, I guess.
Okay, I see now. Yeah.
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 So you've got some key.
First, you deconstruct this parent, and you want to try to it's not easier to understand when you remove the proof. Yeah.
So that's the inputs here, right? Yeah. And then the output is you put the key and the val at the top. And then on this side, you put
the whole L.
The new key val with
yeah.
L, and what used to be here is now here. And then on this side,
yeah. Nice.
So and we can see that this thing is of height 2 or 3, and this one was only of height 2 or 1 or 2.
Yeah. We should write proofs in this way and not in just syntax. It's easy to understand, you see it immediately.
Right. Yeah. So that's a case of how something grew. So they go through and compute the results, but also a proof that the results are correct.
Cool.
Because the proof that this GUI result is correct is that right there.
Now I have a question. How your dictionary is related to this AVL tree?
Okay, so they build a dictionary. I mean, it's reasonably clear how to build a dictionary out of an AVL tree because the nodes have keys and values, right?
Yeah.
So he's saying, in fact, where were we? Where is dict? AVL dict.
So in a sense, your dictionary is not. Oh no, dictionary is already created from AVL tree. Oh,
right. It's created from an AVL tree by ignoring the height.
I just wanted to say that this dictionary, missing some information.
Right.
Okay. Oh, so you really need AVL tree, and not the dictionary, right?
Right. Yeah. So he's saying that I should be able to prove my theorem if I look under the covers. I haven't done that, but we could see what happens if I try. We'll go with 3. I've probably done at least 3 iterations of this.
Do you use external packages inside your project?
Yes.
Okay.
And I did go through some hassle for that.
I was struggling to do it. So.
And in fact, this stuff wouldn't compile, and so I actually had to patch it. So I went through the trouble of forking and patching it and getting Nix to build the right thing for me and all that crap.
Oh, okay. It's not easy. Okay.
Well, there are probably shorter paths, but this is what I did because I've been using.
My understanding is that you install a package like a globally on your machine, but I mean for the user. So
yeah,
like strange. Is this correct or I'm missing something?
Sorry, say it again.
You're installing package for this user, like for the global. Then you install a package.
Yes.
Okay, so this is how it works.
Well, I mean, I did it in a Nix.
It's the Nix shell. Yeah, definitely. Yeah, this is a good idea.
Have I lost my Nix shell window?
Do you maybe have this Nix shell file inside the repository?
Yeah.
Nice.
Oh. So where is?
Is it on your GitHub?
Yeah. Oh, we were probably just there.
Okay.
Branch. Chainmail address branch. Chainmail. Shell.nix.
Okay, nice. Okay.
There it is. Okay, so man, that's loud. All right. So Emacs is my friend. So I will go Control-C, Control-L. That is load the thing. No such file or directory Idris. Oh, evil. Oh boy, have I lost my whole?
And you can mix this deer kind of with mixed shell.
Yeah. What? Lost my marbles. Oh, little a. Ah, there, okay. It's working from here. I don't know why it's downloading stuff, but oh. It's doing that because I told it to use containers.
With specific version or
Yeah. Fetch from GitHub, blah, blah, blah. I think that the original containers guy fixed that bug, so this a lot of this isn't necessary anymore. But
oh, you're specifying your
right.
Okay.
So why won't this work now? There we go. Connection. Okay. Can't find data AVL. That's kind of reasonable. Idris, choose packages. Ugh. Name too long. Oh, this LD preload thing. Crap.
What?
That's some other weird thing. I'm going to exit out of this.
And what this command from Emacs is doing when you say Idris package? Does it modify some project file?
Yeah. So, well, it's going to do that basically. Hold on just a sec. Chainmail. Where was I? Right. And so I try to do Control C, Control L. That is load the file, and it can't find data AVL. Let me try this again. Choose packages, and then let's call it Idris containers. Save package list for future sessions. So that just left some comments for Emacs, and basically what that says is Emacs, when you go and fire up Idris, load the containers doodad.
Oh, I see. It's for Emacs, not for Idris.
Right. There is a way to make a Idris package file, but I haven't done that.
Okay.
Okay, so no holes found means you win. And trying to remember what I did. So here's our theorem. Oh, I guess I'll use the Coke name for fun. Given a key in a dictionary, key and a value, I suppose. So here's our theorem. And then I can do Control-C, Control-L. No such variable dict, so I didn't import it right or something. Okay, so it's saying there isn't any lookup thingy. Let's see if that's the case. Ooh. There's lookup. Oh, a lot of times what happens is that it's actually some other error. So if I say dict.lookup, yeah, you find out that it's actually something else. I think I got my precedence wrong. I never know when I need parentheses when I'm doing Haskell sorts of stuff.
Can you define this as just? I mean, just is a constructor, not a type.
Right.
How can you say that is not nothing?
Say again?
How can you say that is not nothing?
Well, that's the claim here. And then we're going to have to prove it.
But I mean, how can you say this? I mean, you cannot say I will return this constructor. Right?
In Idris, there's no distinction between types and values. There's just things. That's what it means to have dependent types, is that values can occur in types.
Oh, so you're saying this just is not it's on type, like on type level. It's okay. I see.
Yeah, it's a little brain bending, but it's yeah. You have to stop making a distinction between types and values. Okay, so what am I doing wrong here? Lookup is like
you need arrow instead of equal.
No, it's going to return a proof that these things are equal.
Oh, so okay. The whole line is return type.
Yes. Okay, I had too many arguments, just like it said. So I'll try this again. Can't find implementation for ORD K. That makes sense. I didn't tell it that there's a way to order the keys. Add that constraint. Okay. So now it says, okay, that's a perfectly reasonable type to claim, but now you've got a proof obligation, which is basically spitting out exactly what I told it. All right, and then you do Control-C, Control-S to start, and it will start the pattern matching game, and then you can do stuff like case splitting. Control C, Control C. Well, that's interesting.
Yeah.
I probably don't need this anymore since I got the types right.
So whatever you give it as an argument, you will have impossible. Okay.
Okay, so it generated this impossible thing when it was just wrong. No such variable AVL tree. What does that mean?
A make dict is constructor of AVL tree, right? Maybe you need to import AVL tree.
No, it's a constructor here. It's a constructor of trees. Oh, but this is not it.
Okay.
Maybe that's what it's complaining about. Yeah, this is part of life with Idris, is that the error messages are not all that great sometimes. Okay. So the other thing is that you can do is you can sort of say, help. I mean, I could just call that X or whatever.
Yeah.
But it'll give you the type of X.
And what is the shortcut to that it is try to give you the solution?
Control C, Control A. I don't know what it did there. Control C, Control A is attempt to solve whole. So it didn't try very hard. Basically, it just looks in this stack here. There's a bunch of things that you know at this point, and it just looks for whatever type you're trying to fill. It tries to find that type over here and says, oh, you've got one of those. I'll just put this in there. Doesn't search very far. So why do we believe this? Well, we can K-split on trees, right? Maybe we got an empty tree. So we'll K-split there. Oh, so every tree is one of these element gizmos. So now X is actually one of the tree doodads. We'll K-split there. Ah, that was kind of cool, isn't it?
Yeah.
Right, so it K-split the X into empty and node X, Y, left, right. Okay, so in the empty case, we should have an easy job.
So PF is AVL empty.
Yeah, I could K-split to verify that. Yeah. Now maybe maybe it's so easy that the computer will find it for us. Nope. Okay, so what is our X12 thing? With blah, 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 compare. Equals just val.
But is this possible? Is this possible situation when we have empty dictionary?
You're right. I think. Well, no. I mean, it's allowed. Let's see. Yeah, we're allowed to add the key and the value to an empty dictionary. Let's see what the lookup function, how it's defined.
Oh, this is like input dictionary before insert. Okay.
So that's defined as the AVL API lookup.
So now we want to prove that val is equal.
Yeah.
That val be inside the just always in this situation. Okay.
So here's lookup. Oh, we don't really care whether the input dictionary is empty or not. So case splitting here doesn't help all that much, I think. What we care, well, yeah, we do, because we want to be able to grab the first element and compare it with key. Lookup key empty is nothing. Oh, we're trying, oh, we got to get the insert. Oh my goodness, insert's probably some huge thing. Where did AVL dictionary? There's probably a way to say what the heck is this in from here. Idris, get documentation. But that's not what we needed. Where's insert? Yeah, AVL. Yeah. So there's insert is run insert on do insert. And do insert has got 12 cases or whatever in each of those. Some of those are rotate right, which has got a bunch of cases. Oh my goodness. Yeah. I think it's going to end up with like 127 really easy cases. But the other thing to do is to do it.
But can you somehow call insert on this AVL tree and somehow extract this n and say, okay, now I have n plus 1 and
well, I can call what now?
one of these inserts on AVL tree. But I'm not sure. The return type is a type, right? This equality type.
Yeah. I mean, I can do X where and then, or just start messing around here. But you're right. Eventually, I have to come up with REFL or something. Insert key val.
Okay.
T equals. Yeah, you can only write X equals Y if X and Y, you can see that they're the same thing by staring at them. And this thing is like, well, those aren't exactly the same thing. Yeah, I think you basically have to case split over and over and over. Oops.
Uh,
Uh,
so you want somehow use this N. Right.
yeah. Uh, I need to get more things in scope somehow. Okay, so I think we can see that there's going to be a lot of cases with AVL tree. But let's do it with just using, there's another way to represent dictionaries, which is just lists of keys and values. So let's see, hold on.
Just as a list or as a vector? With,
I think list is enough to do it. Oh. Okay. So insert is just going to be sticking the thing on the front of the dictionary. Okay. And then we'll ask it to start for us. And oh, then there's this dependent pattern matching thing where, oh, but we don't have the thing that, we got to compare key to the, look up key value. Oh, right. So, we don't need to be able to sort them. We just need to be able to compare them.
now you have first case when it is empty, right?
Well, we're always looking up into this. So okay, the dictionary can be empty. Yeah, okay. In which case we're looking up our key is here. So I think this is going to be lookup. It's kind of obvious. P is going to be equals.
You will get right the just val as a lookup. Oh, oh yeah. Yeah, but
Yeah.
return type of the lookup is maybe, so is this okay? Because you need just.
Yeah. So that's where we're getting our just right there.
But you don't have the proof for that.
Well, I should be able to substitute this in for this somehow. I wonder if the thing knows that X is always equal to X. I'm not even sure that's true. Let's set that aside for a second. Oh. I don't think it does. Because the double equals is one of these things where the implementation is kind of opaque.
What is the result type of double equals?
Boolean.
Okay. But you want you want type to be result, right? Not boolean.
Oh,
Oh, it has really believed me.
no, wait a minute. Oh, wait a minute. Ruffle of What's the difference between these? Oh, I see. One of them won't reduce in the type checker, and one of them will reduce in the type checker. I don't know what that means. Well, let's go with that for now. Oh, now we're getting somewhere. If key equals key, then just val, else nothing equals just val. Why doesn't it? Okay, let's see. If key equals key, should be able to rewrite that to true. Yeah.
What exactly do you do when you say rewrite? Is this like a lightweight macro?
I think it's a little bit magic to me. Let's see. Rewrite. So basically, if you have an equality proof, you can substitute equals for equals. So they're going to substitute that for that because they know that they're equals.
But you must give in the proof. Oh, okay, okay.
Yeah. So REFL, where x is key, is going to give me a proof that key equals true. Where there's two different kinds of equals. So another thing I don't know.
And from where you're using x?
No, if Working
What do you mean? Sorry.
working with Booleans is a pain. I mean, clearly, if true, then A, else B should give us A, right?
Yeah.
But it's not clear why yet. I have to find the definition of if then else. It's a macro. Where's the?
Oh, you need to supply proof for if then.
Something like that, yeah.
It works like that. Okay.
Shoot, where do they define if then else using syntactic macro? It's some kind of.
Yeah, there is a special keyword syntax, right?
No, it's not spent. It's just using their syntax, their macro thingy. Let's see. Syntax extensions. Where do they actually use one? Oh boy, there's a lot of these. Uh-oh. Oh, I thought it
Oh,
was.
this is sentence. Yeah.
They use delay to make sure you don't have to evaluate both sides. Where did it go? I thought I had seen the definition of if then else using.
I think they present this example in documentation or anything else.
Yeah. Here we go. The underlying implementation of the if then else syntax. Oh, I wrote true the wrong way.
Okay. Oh, so your true with the lowercase is just a variable.
Right.
Cool. But can you now give this if then else function as a proof?
Well, I can try this.
Hmm. Hmm.
So why didn't it know? Okay, I didn't have enough parentheses or something.
Now it's working.
Okay. All right. Wait a minute. Oh, darn. If
And what you had is was function, right? And this replaced if you can just put true there, right?
yeah, well, I don't know why it won't beta reduce.
Oh, this is function, and you have an argument true.
Yeah.
Oh, now I see.
If true, then just vel else nothing. Okay, so I have to rewrite a smaller thing. Oh. What are the odds? Sometimes where doesn't work because you have to give the explicit types and stuff. Let's try this.
Can you say what is X? What are you referring to for X? In calling rewrite ref.
Oh, here. Okay, so when you put curly braces around something, it means that the argument is implicit. But if you want to,
this is the name. This is a name of the variable in definition of a
yeah. So I'm saying,
okay.
I want to pass key in as X. That's how you pass in implicit variables.
Yeah, exactly.
Okay. Rewriting key equals key to true did not change it. I'm never quite certain which is the rewriting true to key equals key did not change it. That's annoying. Because it knows this much. If key equals key, then just val, else nothing. And rewriting key equals key to true didn't do anything? That's annoying.
So it's expecting the if statement, right? If expression. And can we use this if then else function to somehow say yeah. Rewriting x equals x to true did not change type in if x equals x. Well, I wonder if anybody's around to help.
So Edwin was around. I'm not sure if that was today, but that was 3.5 hours ago. Who else have I gotten help from? This Z-Man seems to know what he's talking about. Not sure when he was last around. Yeah, it may be a few hours before somebody answers.
Oh, that was a very nice presentation. Thanks.
Yeah, so it's pretty immature. If I were using, if I just used Coke, then I could actually spend more time on my problem and less on, the tools.
And how long you are using Idris?
Few years. Maybe 2016. There was this stuff about well-founded induction that I spent some time on. Tried to port it from Coke or Agda or something to this. I was basically trying to prove what was it? Greatest common denominator or something. Turned out to be remarkably needed all this really heavy-duty stuff about recursion.
So you already used Coke before Idris?
I've never used Coke. I've read the definitions in some papers and stuff, but I've never tried to write any.
Cool. I found out Idris also around 2017, and I presented like the dependent types on Zagreb lambda meetup.
Say it again.
I was having a talk in Zagreb meetup, lambda meetup, about dependent types in Idris. I was discovering Idris, and I was just,
Pretty cool stuff. Oh, where did I put my gist? There it is. Let's see if Clay Rat is willing to help anymore. Yeah, I guess I could write a different lookup function. You guys have a lot of energy for this. I would have wandered off by now.
Oh, for me, this is like super interesting.
Okay. Okay. Just don't really care. Oh, what? Again, I never know when I need to add parentheses. Unexpected. Oh,
Is it equal or? For the list, it's like in Haskell.
okay.
But this lookup is different than existing one, right? Because although the type is almost the same, right?
Yeah, we're using the actual equals as opposed to the double equals thing that you can do wrong.
Oh, to compare keys.
Right.
Okay, okay. So the result type is the same. Okay.
Right. So this, instead of saying EQ, which goes with the double equals, we're using saying deseq, and that means that there's this function you can compare, these two, and you'll either get yes and a proof that they're equal, or no and a proof that they're not equal. Does that make sense?
Yeah, absolutely.
Okay. Instead of just a Boolean, you get not only the Boolean, but also the proof that they're equal or not equal. Okay, so now,
Or for this lookup, you must provide the proof for a key that is equal, right? Because you are using the keys inside the lookup. This is like argument, right? When you will call this lookup, you will need to provide some kind of proof for a key.
no, what we provide is there's a constraint on the type K that it's decidedly equal. That means for any two things of type K,
you must have instance for the key.
Right. Right. Okay, so that's so far so good, but our claim is syntactically well formed. Now we got to prove it. This is probably impossible. Oh, bummer. just do that, what happens? Okay. Okay. Proving that x is equal to x. Why is this? Oh. Well, what am I doing wrong here?
So dec returns dec type.
Yeah.
And you're constructing this dec type with yes construct.
This is not really what I wanted to say. What I wanted to say is that this is yes. Let's see, where were we? Okay, so
But this is not equal to REPL. I mean, why not? We're saying that XX is equal to yes REPL.
Yeah, this DECIQ thing always gives you back either yes and a proof that they're equal, or no and a proof that they're not equal.
Yeah. So in this case, it will return yes. So this whole thing should be like a REPL. Right?
Should be, yeah, should be what?
Should be REPL. Because you have yes on the left or right side. But they're not. Between yes.
This hurts my brain.
Do you need parentheses when you make a case match? In the upper example, you have. I mean, I don't know.
There. Everything is decidedly equal to itself. It's right there. Okay. Maybe we would have eventually gotten there.
And when you wrote contra, how this is like interpreted?
The contrapositive.
Contra, like on what contra?
Yeah, if this is saying if they're equal, then such and such, and this is saying if they're not equal, then.
I mean, this is only valid when you have two choices, or
It's kind of a mnemonic. You know, it could be called anything. But the contrapositive of if P then Q is if not Q then not P.
okay.
And I'm not sure why they use that, because I'm not sure where the if P then Q is. I'm not sure what P and Q are in this case. Or maybe it's just a proof of the contrary, or something. Anyway, they use PF when it's a positive proof and contra when it's a negative proof.
Oh, I see.
Contra is usually a proof of something goes to void or whatever. So,
Oh, I see. Okay.
It hurts my brain to do this kind of stuff, but
In this case, it's just a variable, right? When you
yeah,
are using it on the right hand side. Okay.
yeah. Okay, but now that we know that the thing we were trying to write is in the standard library, That doesn't give us an equality proof. That gives us, oh, it tells us that dEq XX is yes, ruffle. Oh, what was I going to rewrite it in? Oh, oh, wait a minute. We're way up there.
This looks very similar to example with booleans.
Similar to example what?
With booleans,
Oh, right.
we're rewriting, but
There's this with thing that I don't quite understand, but I'm going to try it.
I understand this as you're calling additional function, and you can just like extend cases, right?
It's dependent pattern matching is what they call it. So it's some piece of magic that's like not in Haskell.
Yeah, yeah.
But it didn't change anything. Did not change it. All right. Flailing around here. Stare at this one more time. Rewriting dEq to ruffle did not change. Don't type.
You are using the old lookup.
Oh.
But is there a difference or no? Hmm. But they should be equal, right? Using the case or
Yeah, let's see if it's just sort of obvious.
yeah.
Oh, just V0.
But now you are not comparing to anything. Or you're doing lookup you're doing lookup on insert, but you're not comparing to this maybe, right?
Say again?
You're doing only lookup. You're not comparing to just one for this empty case.
Oh, right. But it's got just V0 as opposed to just val. Why didn't it it substituted it substituted key in for K0, but it didn't substitute val in for V0.
And you can you mix the names for input arguments for key and val and this type level variables key and val. Do you need to be careful about this?
Yeah, I mean the type here is K. The name of the argument is key. The type here is V.
Yeah, and you have input arguments that are the same name, key and val, right?
Yes, it's completely normal.
They're like shadowing this type level variables.
No, they're playing the same function. This is the name of the argument. That's the name of the argument.
Oh, okay.
I mean, if I do this and say, you know, the computer expects me to use things that way. Why did it substitute? It matched this here. Oh, and it's actually not nothing here, is it? It's doesn't matter because we're in the no, not the empty queue. Rest is empty. Anyway, because it substituted key in for K0, but it doesn't substitute val in for V0. But if I just take your idea,
I see.
I still don't understand why it didn't substitute for V0. Maybe it would if.
This means that he thinks that V0 is different from val.
Possibly, yeah. But it's decided that maybe it's just because it hasn't looked that far or something. I don't know why the rewrite didn't work. Yeah. make another one. Where's the new Just button? It's weird. Rewrite it in REFL. Maybe replace. Ah, now it's not saying nothing happened.
And when you write like this, rewrite in and then expression, where the result of rewrite is really used.
Well, the result of rewrite is this, you know, it's an expression, right? You take this expression, and I guess you evaluate it.
You mean rewrite? Guess this expression. I'm not sure that I understand where is the function and where is the.
We can think of rewrite as doing this. Start with an equation x equals y and a property x to type. Searches for y and p, replaces all occurrences of y with x and p. That is, we're doing a substitution.
Okay.
So this is a proof. This is a proof that DESEQ key is yes, REFL, right? So we're trying to replace DESEQ key with yes, REFL.
I see.
Which should say case yes, REFL of yes proof and give us just V0. All right, I think I got to go take care of something.
Cool.
I'm still mystified by that V0 there.
Yeah, I'm interested when you find the solution.
Yeah. All right, take care.
Yeah. Thanks for the whole presentation. It is super helpful.
Thomas, you want to see robot on Keybase?
Okay, why not?
So
Maybe you can stop recording now. So
stop recording.
yeah.
Okay.
So the whole